directly after the demo, we're gonna have the closing talk. And I think now it's time for me to introduce you to Christopher, my colleague, who has been working a lot on this decentralized demo. And I will hand over to him and let him explain all the nitty-gritty details. So the stage is yours, Christopher.
Thank you. Yes, welcome to the new demo. I will tell you a little bit about what I have done. Let me share the presentation. And turn myself on as well. Okay. So I will tell you a little bit about our brand new demo that I have been working a bit on. This demo is based on an old demo we used to have before, we used for some years. So I'm going to start out by telling you a bit about this, and then tell you about what we've done to improve it and change what the changes are. This demo is sort of designed a little bit like an airport with a swarm of crazy flies flying and the control tower controlling when they fly. So I'm going to tell you a little bit about how these different parts work, and at the end we're going to run a live demo that will be very exciting. So let's start with the old demo. This demo has been around for a few years in various flavors. We have a tendency of hacking demos when we go to fairs or conferences. We start out with something and then we tend to improve or change them over time, because sometimes you don't have that much to do in the fair, so then we maybe spend some time on hacking around a bit. So the old demo is a hybrid implementation. Part of it is running in the Crazyfly, and the other part is running in a PC with a Crazy Radio. So the part that is running in the Crazyfly, we call that the pilot, and that is responsible for flying a trajectory, while the control tower on the PC is sort of managing the swarm and telling the pilots when to take off and land and so on. We use the Lighthouse positioning system and for positioning, and this is like the basic idea of this demo from the start was to have a nice and simple kit that we can bring to a conference, for instance, and that should be easy to set up and hopefully run without too much need of attention and maintenance. So I mean, the dream scenario is that you turn it on in the morning and it just flies all day. So I will show a short video of the old demo to give you an idea of what it looks like. So here you can see one crazy fly going up, and it goes down in a spiral, and then goes back to its charging pad to recharge the battery. And then at the same time, the next crazy fly takes off to run the same spiral. And you can also see that the crazy fly here missed the charging pad a bit, so it takes off again and repositions to make sure it's charging. We will also get a quick view of the control tower on the PC soon. So yeah, we had a simple UI telling us about the status of each crazy fly, if it's flying, landing, charging, charged, and the accumulated flight time and things like this. Yes, and this demo has been with us for a while, and it's been very, I would say, very useful. So a quick run through of the pilot and control tower. The pilot is an application on board of the Crazyflie. It is designed as an Crazyflie app, so it's an out of tree compiled app. It flies a spiral trajectory, but this is pre-programmed, so that's the only thing it can do. So when it takes off, everything is deterministic. It just flies its trajectory and then goes back to the charging pad. And we are sampling the position at takeoff time to know where to go back. And this has turned out to be a really good trick, because then it's not that important where the pads are located. So we can just pretty much put them anywhere on the floor and put the Crazyflies on them and start the demo. The charging on the pads is done with the Qi charger deck, so that's like wireless charging. Yeah, and as we could see in the video, if the Crazyflie, it detects if it's not charging when it has landed, and then it sort of takes off again and tries to reposition to make sure charging is actually happening. So it's pretty straightforward. And the control tower is also pretty straightforward. In this setup, we have a bunch of log variables that we track in the Python application in control tower to monitor battery levels in the Crazyflies and the state. And then the control tower determines when the next Crazyflie can take off. And the commands that we send are very simple. It's like take off or land or things like this, but there's not a lot of communication going on. We also had a few different modes where we could fly more than one Crazyflie at the same time. I think we could do 4 Crazyflies in the same spiral by slotting them in different, to avoid collisions pretty much. Or we could fly several spirals in parallel, side by side. Yes, so that was the old demo. Now let's look at the new flavor. And what we wanted to do now was to get rid of the PC pretty much and have a decentralized control tower. And this means that the Crazyflies have to somehow agree on when to take off. And we wanted to handle this with the peer-to-peer communication. Obviously, we would like to avoid collisions, and we would like to keep the demo running, so the next Crazyflie slots in as tight as possible to the previous spiral to have a continuous flight and like a demo that is nice to watch. So yeah, how did we end up? What happened? The pilot part is actually very similar to the old demo. That code is not changed a lot. There's some details in the takeoff sequence, but otherwise it's essentially the same thing. So it's still flying the same spiral. It's a simple state machine that is so the distributed control tower tells the pilot that it's time to take off, and then it starts to flies its spiral twice, and then go back to the charging pad and lands. So not a lot of changes, but we will take a look at the state machine for the pilot. When we turn the Crazyflie on, it makes sure that it has a position lock, waits for the Kalman filter to converge. And then it enters a standby mode, where it's pretty much idling, just waiting for something to happen. And when the control tower tells it to take off, it takes off, goes into the center of the spiral, flies the spiral twice, goes back to the pad, lands, and checks the charging. If charging is okay, everything is fine, it goes back to standby. If it's not charging, it takes off again and pretty much just goes to the same position that it took off from and tries to land again. And this is because the landing is sometimes a bit shaky, so it's not always landing exactly at the right position. Usually it managed to do it after a couple of times. We also have these 3D printed landing pads with a slight slope to have a, let's call it a physical centering of the crazy fly to make it slide into the right position. Okay, so let's go to the control towers, which is maybe the more exciting part. This is also implemented in the crazy fly now in the same application, but it runs in a different timer. We use peer-to-peer communication to talk between the crazy flies. And the distributed control tower keeps track of a shared swarm state. So for this to work, all of the crazy flies need to agree on what the current state is in the swarm. I will talk more about what this state actually contains, but this is sort of the key of this application. And in one sense, this monitors the flight of the other crazy flies, because the state tells each crazy fly what the other crazy flies are doing. And the distributed control tower knows about the battery level in each, not of the battery level in the other crazy flies, but in its own crazy fly. So when the battery level is fine and it knows that it maybe can fly because it knows the shared state, then it triggers the pilot to take off. So there are a lot of similarities to the old control tower, but the main difference is that it's decentralized now. So let's look at the different parts. Communication is obviously important, and we use the peer-to-peer framework that is in the crazy fly. This functionality is pretty basic. I think we still consider it to be experimental, and this is actually broadcast functionality. So it's not a unicast thing where one crazy fly talks to one of the other crazy flies. Obviously, this is possible to implement in the broadcast network because you can add an address, but you have to do it on the application level or in the protocol. So if you want unicast, it's possible to do, but in this application, we use pure broadcast. And since the radio cannot both receive and transmit at the same time, we had to come up with some sort of mechanism to avoid or minimize packet collisions on the radio. And the scheme that we choose was to use a time-slotted scheme. The communication here is based on transactions. So one crazy fly initiates a transaction by transmitting a message, and then the other crazy flies in the swarm respond to this transaction. So this is sort of the layout of pretty much all the communication. And the way we did it is that when a crazy fly receives a transaction, the start of a transaction, it knows its own ID. There's IDs 0 to 8, and they use the ID to know in which time slot it should send its response. And we have pretty large time slots; they're 20 milliseconds long. But this is a very sort of simple scheme. And as you can see in this example, node 3 starts a transaction, and then the first crazy fly responds, and then the second one, then the third one, and so on. But since this is broadcast, all the other crazy flies can also hear what they are responding. So this is a feature that we are utilizing in some parts of the implementation. That it's not only unicast, it's broadcast. Right, so that's the basic of communication. Now it turns out that packets are lost in the real world. That might not be too surprising, but We found out initially I just used one packet per. I just sent one packet, but it turned out to lose a little bit too many packets. It sort of worked, but the system had to use a lot of time to handle lost packets in various ways. So we ended up transmitting each packet 5 times. So we do this in the slots very quickly. So instead of sending one packet, we send a burst of packets. So in the similar example as before, we can see that node 3 is starting the transaction, but now it's sending it 5 times. And same thing for the responses. They transmit bursts of packets. So, and to handle this, we added a sequence number to the packets. So a receiving application can use the sequence number to determine if it already has handled this particular packet. Pretty straightforward solution that it's pretty common in broadcast applications. Finally, we have a simple mechanism as well to avoid transactions to start, two transactions start at the same time. So whenever a Crazyflie receives a transaction, it starts a holdback time. And this holdback time, they are visualized with the red lines here in the graph. So during this holdback time, the Crazyflie is not allowed to start a new transaction. And we randomize the holdback time a bit to make it less likely that 2 Crazyflies start a transaction at the same time. So again, in this example, node 3 is sending a transaction, and the other Crazyflies randomize a holdback time. And we can see that node 2 is the first Crazyflie where the holdback time expires, and if Crazyflie node 2 here, wants to transmit some sort of start transaction, this is the time when it could do it. Also pretty straightforward mechanism. I haven't really done any proper measurements on how many collisions we get, but it seems to work pretty well. Yes, the next part of the distributed control tower is that we need to agree on the state of the swarm and the world. And this is what we call the shared swarm state. We are using a swarm state that contains locks. A lock represents a flying Crazyflie. And as long as this lock is taken, no other Crazyflie can fly at the same time. But we sort of made a tweak. So we set an expiry time for the locks. So one Crazyflie can say that I want to fly, so I'm going to take one of the locks, and I want to keep this lock until some specific time. And the benefit of having a timeout lock is that we do not have to release a lock explicitly. That would require some sort of communication, which would make it more complex. So this is like a pretty neat way to simplify communication. So pretty much all communication is about taking locks, but not releasing them. And the benefit is also if like one Crazyflie maybe crashes or dies, then it doesn't have to release the lock, and we don't risk having locks hanging, and we don't need to handle that problem. The swarm state contains 3 locks. I actually think it might have been enough with 2 after the last changes I did, but it really doesn't matter. So each lock each lock contains a node ID and an expiry time. And this is representing a flying Crazyflie or a Crazyflie that will fly soon in the future. So it has booked its flight time pretty much. Yes, so this is the information that is shared in the swarm and that must not be corrupted between the Crazyflies. So there is also a part of flight planning. So when a Crazyflie figures out that my battery is charged and I'm ready to go, it checks the current swarm state, and maybe it sees that, ooh, there is a free spot here. I want to fly, I want to take off. Then it has to plan when to take off. And I have done some variations on this flight planning that were more or less exciting. Originally I wanted 2 Crazyflies to fly at the same time, but it turned out to be a little bit too. We got a little bit too many problems in Crazyflies crashing due to downwash. So in the version that we have now, the next Crazyflie takes off when the currently flying Crazyflie is going back to its pad. So they are sort of taking off and landing at the same time, but they're not really flying at the same time in a spiral. We had that for a while, and it looks pretty neat, but yeah, there's some problems when one Crazyflie is maybe going back to the pad and the other one is passing above in the spiral. But yeah, there are different ways to do this depending on how exciting you want the demo to be. So the final part of this is how to agree on the shared swarm state in the swarm. How can we make sure that they all have the same idea of who is flying when? And we have based this protocol on, it's loosely based on Paxos, which is some sort of standard idea of how to do it. It's pretty much based on two-phase commits and majority decisions. So we have 9 Crazyflies in this swarm. So if 5 of the nodes agree on something, we have consensus, and then this is the new truth. I will not go into the deeper details of this type of distributed consensus. First of all, I'm not an expert on it, and this also tends to be pretty complex. As I mentioned before, we use broadcast instead of unicast, and this is actually used to our advantage in some cases because we don't have to retransmit the information as much as you maybe would have had to do in a unicast situation. Also, as mentioned before, there are lots of packets lost. So there are a lot of cases where the nodes do not really agree on what the world is like, but it's important to have a mechanism that makes sure that at least they understand that they don't have the same view, and then there must be mechanisms to restore a shared view. We assume that all the nodes in the system are nice, which means that there are no rogue nodes that might transmit bad data to sort of mess up the world. The drawback of this approach is that we also assume that the code is bug-free, but of course it is, isn't it? Okay, so let's look at a couple of examples of how it works. So we have the 9 nodes here. And in this example, node number 3 wants to start a new transaction. At this stage, probably node 3 has figured out that the battery is charged and it wants to fly. So let's start this. And like I said, this is a 2-phase commit thing. So this is the first phase where pretty much the goal is to agree on what the current state is. And this is sort of the sunshine case. Everything is as expected. So node 3 transmits a message called proposition. This message contains a unique ID, 17 in this case. These IDs must be unique and they must be always increasing and never reused. So node 3 transmits a proposition with ID 7 or number 17. And all the other nodes, they say that, oh yeah, this looks perfect. I give you a promise. And this promise, what this means is that they will never act on another message with a lower ID than 17. So 17 is now the last sequence number or ID. So they all transmit this message, and node 3 receives these, and it gets more than 5 approvals for this, which means it has majority. So phase one is finished, and they now know that they have the same idea what the state is. So node 3 proceeds to phase 2. Phase 2 is when node 3 now knows that it can change. It's okay to change the state, so it quickly does a flight planning to decide when it wants to fly. It updates the state and transmits the new desired state together with the number 17 that they agreed that was the last number. And all the other nodes get this state update. And they promised that 17 was okay, so they all say, perfect, you are good to go. So they send back an accept. And when node number 3 has a majority of accepts, it knows that the new state consensus state is set in the swarm. Then it knows that it can act on this new state, which means it's free to take off. So at this stage, the control tower can tell the pilot in the crazy fly that you're good to go. Let's fly. So this is like the sunshine case. Everything is fine, but obviously this is not maybe what happens most of the time. I will not go into all the corner cases, but I made an example here with some random problems. So we're back at phase 1. Node number 3 wants to fly, so it sends a proposition with ID 17. And we have a bunch of different cases here. Node number 8 completely missed this message because it was lost, so it's not responding at all. Node number 4 and 6 and 2, they all think that we are at ID 17. So they say, yeah, fine, promise, I gave you a promise of 17. But interestingly enough, they actually missed some messages before. So node number 7, for instance, has got a later message. So number 7 has already made a promise for 4711. So number 7 is going to return, say that, no, this promise, I cannot promise you this because we are already at 4711. So sorry, not okay. And number 5, 0, and 1 seems to do this pretty much the same thing here. So the end result is that number 3 did not get the majority, but he got some information about what the latest state is. So now he knows that number 4711 is the latest number and that what the current state was, at least according to number 7. And now he can use this information to update his own knowledge about this current state, but he is also using it to help the other nodes in the network by retransmitting the latest known state together with the latest known number to all the other nodes. So they also can update their knowledge about the current state. So this is a mechanism that is used to update the swarm to have the same idea what the state is. Yes, so this is pretty much everything. We're going to look at the state machine in the control tower as well. It's typically in the idle state, and after a while it goes to check the battery level as well as the swarm state to see if there are any empty slots, if it's okay to fly. If it's not, it goes back to idle. But maybe at sometimes the battery is charged, everything is good. So then it sends a proposition to the peers and goes to the next state, which is a wait for promise. It waits for the promises to come back to see if it gets a majority. If it gets a majority, it plans the flight and sends a state update with a new updated state. and then waits for to get a majority of accepted state update. And if it gets this majority, it moves on to flying, and then it takes off and flies its trajectory, and then goes back to idle. And then there are some also, as you can see, some ways back in this state machine if it did not get majority, and so on. I hope this is crystal clear. I will just do a quick run through of what we're using in this demo as well. Hardware-wise, we have 9 Crazy Flies with Lighthouse decks and Qi chargers. We have 2 Lighthouse base stations, and we have Qi chargers from IKEA with 3D printed landing pads. I use my computer with the Crazy Radio to just start and stop the demo, but otherwise it's not used for any control. I also have a sniffer on my machine, which is implemented through a Crazy Fly to be able to see the messages going through the air. The code is available on GitHub, of course. So if you want to check it out, you can find the URL here in the presentation. So yeah, before we start the demo off, what did we learn? Yeah, we learned that we lose more packets than we were thinking, especially on the floor in our flight lab. We're not exactly sure why. It's possible that the floor there's metal under the floor maybe. So this was slightly unexpected. It's also pretty hard to debug this type of application because obviously there are multiple nodes doing different things. If they are flying, it's a bit tricky to get logs at the same time, because if we connect to them with the radio, there's a risk of messing up the peer-to-peer communication. So debugging in general was a bit tricky. I've done some various tricks using USB connections and stuff instead. And also, if I look at the data from the sniffer, I can only see what the sniffer is seeing. So if I do not get a packet from one of the Crazy Flies, I do not know if it was because the Crazy Fly didn't send it, or was it because the sniffer didn't receive it. So there's a lot of unknowns in the debugging part. Distributed consensus is also tricky because there's a lot of weird corner cases, and there's a lot of stuff going on with a lot of nodes. So it's also tricky to understand what's going on. And yeah, like always, we found some bugs related to peer-to-peer communication. There was some issues with the high-level commander as well. But that's good, because then we can fix them. But like Anoa mentioned earlier today, that we often refer to this as design by demo, or it's a really good thing for us to write demos, because this is when we have to fix all these things, and we see what the problems are. So now it's time for a live demo. How exciting. Let's see. I will start by switching my I will share the sniffer output as a start, and I will put on top of this, I will put a video of the swarm itself, hopefully. So can you see the swarm down in the corner and the sniffer output? Now I'm going to go to my Crazy Fly client, and I'm setting a parameter in one of the Crazy Flies to enable it. And this will trigger all the other Crazy Flies to join the fun, and they will start to talk to each other, hopefully, and try to find a consensus. Now you can see that there's a lot of messages going around, but they apparently found a new consensus here. So the locks seem to be taken for node 3, 0, and 5. with 3 timeout times. And now the first crazy fly is flying. So let me switch this to the video only. So now this is going back and the next one takes off. And now that the first slot is free, now you cannot see the sniffer output, but there hopefully there is some new discussions about who can take the new slot that was just free. Yeah, so now this one is getting close to the end, and hopefully another one is gonna get ready to take off. The landing was not perfect. Luckily, I have an assistant that restarts them, put them back in the swarm. The cool thing is that they're just gonna pick up where in the conversation where the other guys are and be part of the fun again. So let's see how it goes this time. It seems to work pretty well. Now we can see that the crazy fly that just landed missed the pad, so it takes off again and tries to reposition and land again. Yes. I think that's pretty much it. I'm not sure how do we do with questions and stuff like this, Tobbe?
Yes, can you hear me?
Yes.
Yeah, so a bit ahead of schedule. So either we do a super long question and answers, or we could also do a quick one and maybe move to a Meeble room because next thing is starting at 5. But maybe let's start with some questions. So please write anything in the chat box, and we'll see how much time is left over. So first thing, Christopher, we got a question from Wolfgang. How long can it fly for?
The swarm or each crazy fly?
I guess how long the demo, maybe the swarm, it says here.
It's gonna fly until all the crazy flies have crashed. But apart from that, forever. I would say, or until the motors are worn out or the batteries are worn out, maybe.
Yes. Yeah, the tracking is a bit unreliable at the floor at the moment. That's why we see some crashes down there. But with the good tracking at the floor as well, it would probably run for days, I think. It's very consistent. Right, its crash at the bottom. Maybe we have a reflection in the TV. Maybe.
I don't know.
Who knows? Yeah. It says also, do you test packet loss with the crazy flies not flying?
Yeah, I had a few different setups. One was to use the crazy flies in the swarm, but I disabled the actual flying. I just let them sit on the pads, and then I connected. I had USB cables to all the crazy flies to be able to get a lot of data, and then I pretty much logged everything into one sort of unified log to be able to see what they all saw. This was one setup, and we also have an old like test setup with 10 road runners, which is it's another product we have, which I used as well. Same thing, they're not flying, but it's easy to connect to them and check them out. But yeah, I haven't done any sort of deeper analysis of how often we miss packets or exactly which packets we miss. I pretty much just sort of figure out those. It looks like we missed a little bit too many. Let's try to send some more to see if we can fix the problem.
Continuing from Michael, do you account for any directionality of the NRF51 antenna?
Nope. We just transmit and hope for the best.
Yeah. Yes. Another question from Wolfgang. How does the implementation differ from textbook Paxos? Is there a plan to have Paxos as part of the peer-to-peer API?
There are no such plans. How it differs from Paxos, I think Paxos pretty much doesn't support update of state at all. So that's an update or an addition. And I also use, like I mentioned, some features because we have broadcasts and we can pick up some information that is not available in normal Paxos by listening to messages going around in the air as well. In Paxos as well, you're not allowed to have, or either the IDs that are in the packets must be always increasing and unique, and they should be persisted between restarts. We do not do that. So when we restart the Crazy Flight, it restarts at a very low number. But it usually works. It might not be foolproof. I mean, it's also possible there are some holes in this implementation of the protocol as well. Like mentioned, it's tricky business, the distributed consensus.
Yeah, and then the next question then from Wolfgang, how do you synchronize the CF clocks for the time slotted communication?
Yes, yeah, I forgot to mention that. So very good question. They're pretty much two. Yeah, so to take one step back, the clocks in the Crazy Flies are not synchronized at all. They run pretty much at the same speed, but not exactly, and they might have been started at different times, and they do not have any sort of idea what the global time is. So what I do is that when a transaction is the start of a transaction is received, we just sample the current time, and then each Crazy Fly knows what ID it has, and so then it can figure out the time slot it should transmit the response in. So that's pretty straightforward. The other problem is the shared state, which contains a timeout. And I mean, since they do not know anything about the global time, we could not say that this lock expires at 15:33:24 or something. So what we do instead is that the times in those packets they are relative. It's relative. So it's relative to when the packet is transmitted. Now it's pretty much received at the same time as it's transmitted, and the accuracy is good enough. So the transmitted state contains the ID of the Crazy Fly, but the number of milliseconds remaining until the lock is expiring. In the Crazy Fly, when it receives this, it's converted into the clock of that particular Crazy Fly to be as an absolute time, of course. So that's the way it's done.
Yes, so I have some questions as well regarding scaling. Do you have any ideas about this?
How big can the swarm become?
Yeah.
It doesn't scale. This is pretty much made to work for 9 Crazy Flies. I mean, you could probably scale it a bit by extending the time slots and the number of slots, of course. But there's going to be some sort of limitation on how many. Oh, now it goes bananas. There's going to be some sort of limitation of how many slots you can fit in within a reasonable time. I mean, you could optimize this. Now they are 20 milliseconds long, the slots. So you could probably make them a little bit shorter. But there's going to be some upper limit that is not very high, I think, for scalability.
So I guess then like radio communication is one of the biggest hurdles.
Yeah, I think so.
It will take too much time and to reach consensus, or there will be too many Crazy Flies talking. You would have to have a new scheme that overcomes this.
Yes. Yeah, I haven't thought too much about this actually. I wanted to solve a problem for 9.
Yeah. Yes. Another thing, working with many, do you have any tips developing for them scripts or stuff that makes it easier?
Yes. Like I mentioned, it is a bit tricky from time to time to get the data you want out. Yeah, sometimes I used USB and used the normal console logging in the Crazyflie. But by connecting via USB to all the Crazyflies at the same time, I could get all the logs into the same. I merged everything into one just gigantic log to be able to see where the packets and when the packets received in different Crazyflies. This obviously does not work when you are flying, but the upside of this is that you do not use the radio, so it's free for the peer-to-peer communication. Another thing that we never used but we discussed is to possibly use LEDs or some other pins on the bus to trigger like logic analyzers. So for instance, you could like set the pin when you receive a packet or when you transmit the packet. This is also like for really low level debugging and timing measurements. Yeah, the sniffer that I have, I choose to use a Crazyflie as a sniffer. And the reason is that the peer-to-peer packets can be larger than the packets supported by the Crazy Radio. Actually, I'm not using that much data in the packets right now, so they are short enough to be received by the radio, but that's how I implemented it anyway. So there is a sniffer Crazyflie that pretty much just gets the peer-to-peer packets and pushes them out on the. There's a specific app layer port that is easy to decode or receive in the Python lib. So I just forward all the data for the sniffer to see. Yeah, I don't know. Maybe those are like the main strategies.
Yeah. Also, I know we use when flashing and stuff, we make Python scripts to kind of so you easily can upload the code to all Crazyflies in the swarm, which helps a lot. Which I think is available under one of the tools folders on the Crazyflie former or in the lib.
Yeah, and it's also in this demo branch in that directory. There is a script called cload all, which is going to flash all 9 Crazyflies.
I know there's a lot of trial and error in the end, and you need to be flashing, change something, see what happens, and flash again, and then it takes a lot of time if you have to connect to each Crazyflie after another.
Yes.
So this helps.
Yes, it does. And also the charging pads are very good for this type of work, since you don't have to change the battery all the time. So they can just sit on the pads and always be charged.
Yes, that helps a lot.
Yes.
Well, I think we don't have any further questions. Me neither. So I would like to thank you very much, Christopher, for this great demo and talk. We have about 10 minutes until the